Hi, welcome to Lesson 4 of IB Physics at Edu Solutions Institute. So today's lesson will be focusing on frictional force. Now, we are continuing from forces because last class we looked at representing forces and we looked at free falling objects, right? And the nature of the forces that are acting on objects when they're in motion. Now, today we'll be continuing with that same principle of motion and forces, but to look at frictional force and how it affects objects moving or stationary. So, the nature of frictional force is from contact of two objects touching each other, and this is a type of a resistive force. Hence, it will always be in opposite direction to your applied force. But what that means is if we are pushing an object over that direction, then the frictional force will be trying to put it in the opposite direction. Now we have two types of frictional force. We have the dynamic and the static frictional force. Now the word dynamic has to do with motion. So this is a frictional force that we have when an object is moving. So it's that resistive force that's trying to slow it down or to stop it. Now with static frictional force, this is the force that is there when an object is stationary. Now when you're applying a force, if you start very small, then you have the static frictional force that keeps it stationary, right? Until you can overcome that frictional force with your applied force, then the object starts to move. So static frictional force is that resistive force that keeps the object stationary until you can apply a force that's greater than that force, right? So in that said, we have two equations or two relationships that we use. For dynamic frictional force, we say that the frictional force of dynamic friction is equal to the coefficient of dynamic friction times R, which is your normal force, right? And for the static, it's more of a relationship that says the frictional force is less than or equal to the product of your static coefficient of friction times your normal force. So this takes us into what exactly is your coefficient of friction. Now your coefficient of friction is a constant based on the surface that you're moving on. So for ice will have a different coefficient than if it was moving on water, or if it was moving on piece of board, or if it was moving on piece of concrete. So these are different surfaces, and if it's smooth, then the coefficient of friction is different than if the surface is rugged. So if you're getting more resistant forces from that surface, then the coefficient is a bigger number. If you're getting less resistive force, then the coefficient is a smaller number. All right. Now, notice that for static, it's not an equal sign. What this means, it's a range. For the static frictional force is a range based on your applied force. So it's a range from between 0 to the product of your coefficient times your normal force. Now, we have three diagrams here that we will use to represent how we can relate static friction or dynamic friction to different situations. So the first situation here is when an object is on a horizontal platform. Now, this object is horizontally, so we know based on last week's lesson that there is a weight going down, and that weight is also equal to your normal force going up. Right? So if we apply a force onto this box, let's call that F, to push this box, then we know that there is a frictional force that is going to be provided or produced. That frictional force is equal to the coefficient of friction, dynamic friction, times your normal force, which is your weight. So in this case, we could replace this R with M times G, because that is your weight. And that gives you your frictional force. Right? So this one is simple. Now, if your frictional force is there and your applied force is F, then that means we will have a net force. And that net force would be the one that's pushing it forward minus the one that is resisting, which is your FF. So that's a relationship that we will use in these set of questions. Now, depending on the motion of the object, if the object is moving at a constant speed, then that means this net force is zero. And that means F would be equal to frictional force. But if the object is accelerating, then that means these two values are different. Hence, you will get a net force. All right, let's look at our second. Now, this is object sliding down an inclined plane, right? And it's sliding down at a constant speed. Now, at a constant speed, that means we will have an angle for this inclined plane. We will have our forces or weight vertically downwards, right? We have our normal, which would be 90 degrees to the surface, and that's R. So this is 90 degrees to the surface. Now, based on this, what we're going to realize is that the weight will have two components to it. The weight has a Y component and an X component because it is on an inclined plane at an angle. So unlike this that only has a Y plane, this weight will be acting in both the X and the Y. So therefore your X will be pulling it down the incline and your Y is opposite to your normal force. So in this case we can say WY is equal to your normal force. Unlike this where W is equal to R, the Y of the W is equal to R because they're opposite forces causing the object not to go up or down. So that means if we replace WX, W is adjacent to the angle, so that would be W cos theta equal to your R. So this is one relationship that we will use in future references. Now, if we notice what is pulling down this object, the WX is pulling it down, so hence we have a frictional force that's trying to pull it back up. It's at constant, so therefore what we know is that WX is going to be equal to your frictional force. So your maximum frictional force provided is going to be equal to WX that causes the object to move at a constant speed. And that would relate that WX is opposite, so that's W sine theta will be equal to your frictional force. Alright? And therefore, if we want to identify your net force, it's going to be one that's pulling it down, WX, minus the one that's trying to pull it back up, which is FF. So in this case, because it's constant speed, then your net force is zero. That means these two are equal. And that's what we see here. All right. And then finally, instead of going at a constant speed, we're going accelerating. So therefore, just drawing back the same forces because it's an inclined plane. We have the same set of forces, WY, WX. And we also will have our frictional force. So that means the same thing applies. R WY is equal to R, right? But in this case, our F net is WX minus FF. So they are not equal this time. So we can put this here that they are not equal. They are not equal because the object is accelerated. Accelerated means we have to have a net force acting on the object. Right? So these are three main situations that we will look on in the future of looking at frictional force and how it affects motion of objects. Right? Now, in certain cases, let's say in addition to this, we had a force pushing down the object. If we apply a force, an external force, all that means is that we include that in our equation. And in that case, we will have that F net would be equal to, if this is going down just like Wx, so it will be F plus Wx. And then we subtract the opposing force, which is your frictional force. So it doesn't matter which forces are there. All we need to know is we add the ones that are going in the same direction and subtract it from the opposing forces. And that will always give you the correct equation to use, and we can just put in our numbers to find our unknown. Alright, so that's it, the end of today's class. Hope you understand a little bit more about our frictional forces and how they affect motion. So see you next week. Thanks for watching.